Long before cities rose and civilizations built their monuments, before writing emerged or agriculture transformed human life, there was counting. Our earliest ancestors looked at their children and counted 1, 2, 3. They looked at the days between moon phases and recognized repeating patterns. They gathered food and needed to know if they had enough. And so counting was born not from mathematics textbooks, but from the fundamental human need to understand quantity in the world around them. When you count, you are participating in perhaps the oldest intellectual activity of our species, something so natural that even infant minds grasp it instinctively. One apple, then another apple, and somehow this becomes 2 apples, a transformation that is both obvious and miraculous when you really contemplate it. The concept of one is simply the recognition of a single thing, distinct and complete. It could be one breath, one heartbeat, one moment of peace. There is something beautiful in the singularity of one, the way it stands alone, whole and sufficient. Then comes 2, and with 2 comes relationship, comparison, the beginning of pattern. 2 is symmetry, balance, the way your lungs work together, the way day follows night. 2 is partnership and dialogue, question and answer, in and out. Moving to 3 brings stability, the triangle that cannot wobble, the beginning of true complexity. 3 points define a plane, 3 legs make a stable stool. 3 creates the possibility of middle ground, of mediation between extremes. As we count upward, 4 brings squareness and solidity, the cardinal directions that orient us in space, the seasons that structure our year. 5 arrives with the fingers on your hand, making counting tactile and personal, something you carry with you always. 6, 7, and 8 and beyond, each number carrying its own character, its own flavor of existence. Ancient peoples noticed that certain numbers appeared repeatedly in nature, that 5-petaled flowers were common, that 6-sided snowflakes fell from winter skies, that patterns emerged not randomly but with structure and meaning. To count is to acknowledge this structure, to say that the universe is not chaos, but ordered, predictable, knowable. As you lie here now, you can count your breaths if you wish, slowly, gently, without effort. 1 breath in, 1 breath out, 2 breaths total, 3, 4. There is no destination, no final number that matters. The counting itself is the point. The recognition that each moment is both unique and part of a sequence. In this way, counting becomes meditation, an anchor for consciousness, a gentle repetition that asks nothing but offers much. When humans first understood counting, they quickly discovered addition, though they would not have called it by that name. Addition is simply the mathematics of bringing things together, of combining, of gathering. Imagine our ancient ancestor with 2 berries in one hand, then finding 3 more berries and combining them, suddenly possessing 5 berries total. This simple act of combination, of seeing that 2 plus 3 make 5, is addition in its most pure and natural form. There is something deeply satisfying about addition because it reflects growth, accumulation, abundance. When we add, we are always moving toward more, toward fullness, toward completion. Consider how gentle this concept truly is. If you have 2 moments of peace in your morning and 3 moments of peace in your evening, you have experienced 5 moments of peace throughout your day. Addition allows you to recognize and value this accumulation. The symbol we use, the plus sign, looks like a crossing of paths, a meeting point, which is exactly what addition represents. 2 quantities meeting and becoming one larger quantity. In the early days of written mathematics, people used all sorts of methods to show addition. Some drew pictures, adding 2 sheep drawings to 3 sheep drawings and counting the total. Others used tally marks, simple lines that could be grouped and counted. The Egyptians, with their hieroglyphic system, would write number symbols side by side to indicate addition, understanding that physical proximity on papyrus represented mathematical combination. The beauty of addition lies in its certainty. 2 plus 3 will always equal 5, not sometimes, not usually, but always, eternally, regardless of who does the calculation or when or where. This unchanging truth is profoundly comforting. In a world where so much is uncertain, where change is constant and predictability rare, addition offers absolute reliability. The numbers may change. You might add 4 and 7 or 12 and 19, but the process remains identical, trustworthy, faithful. Addition also has wonderful properties that make it even more soothing to contemplate. For instance, the order in which you add numbers does not matter. 2 plus 3 gives the same answer as 3 plus 2. This is called the commutative property, a fancy name for a simple idea. You can approach the addition from either direction and arrive at the same destination, like 2 paths up a mountain that meet at the summit. There is flexibility here, freedom, the knowledge that there is more than one right way to proceed. Similarly, when adding 3 or more numbers, you can group them however you wish. If you need to add 2 plus 3 plus 4, you could first add 2 and 3 to get 5, then add 4 to reach 9. Or you could start by adding 3 and 4 to get 7, then add 2 to reach 9. Same answer, different journey. This is the associative property, and it reflects another comforting truth that mathematics offers. The destination is certain, but the path can be chosen according to what feels most natural to you. Just as addition is the mathematics of gathering, subtraction is the mathematics of balance and adjustment. Where addition grows, subtraction refines. Where addition accumulates, subtraction creates space. Subtraction is not about loss in any negative sense, but about finding what remains, about understanding difference, about recognizing change. Imagine you have 7 smooth stones and you give 2 to a friend. How many stones remain with you? 5 stones stay in your possession. This simple question, this act of determining what remains, is subtraction. The minus sign, that simple horizontal line, represents removal or comparison, a boundary between what was and what is. In nature, subtraction happens constantly in beautiful ways. The tide comes in with 10 waves and recedes with 10 waves, and the beach remains. A tree has 20 leaves, 5 fall in the wind, 15 remain dancing in the branches. These are not tragedies, but natural cycles, and subtraction allows us to understand and quantify these cycles. Ancient merchants understood subtraction as fundamental to trade. If a merchant started the day with 30 fish and sold 23, subtraction revealed that 7 fish remained. This was not advanced mathematics, but practical wisdom, the ability to track resources and make decisions. The relationship between addition and subtraction is like the relationship between breathing in and breathing out, 2 halves of one process, inverse operations that balance each other. If addition asks what happens when quantities combine, subtraction asks what quantity must be combined with one number to reach another. If you know that 3 plus something equals 8, subtraction helps you discover that something is 5. This inverse relationship means that every addition fact implies a subtraction fact. Knowing that 4 plus 5 equals 9 automatically means knowing that 9 minus 5 equals 4 and that 9 minus 4 equals 5. These relationships are not separate pieces of information, but connected understanding, a web of meaning where each fact illuminates others. Subtraction also allows us to understand distance and difference in profound ways. If you are on step 3 of a staircase and someone else is on step 7, subtraction tells you they are 4 steps higher. The difference between the temperatures on 2 different days, the gap between 2 ages, the space between 2 points in time, all these are revealed through subtraction. In this way, subtraction becomes the mathematics of comparison, helping us understand relationships between quantities. There is a meditative quality to working with subtraction, slowly and gently. Imagine starting with 10 and peacefully removing 1, leaving 9, then removing another, leaving 8. Each subtraction is like releasing a weight, like exhaling fully, like letting go of what no longer serves. 7, 6, 5. Counting down feels different from counting up. Not worse, simply different, like descending a mountain after reaching its peak. Both directions have their purpose, their beauty, their place in the journey. Multiplication, when encountered with peace and patience, is nothing more than organized addition, a shortcut that nature itself seems to prefer. Imagine you have 3 baskets, and each basket contains 4 apples. You could count all the apples individually, 1, 2, 3, 4 in the first basket, then 5, 6, 7, 8 in the second, then 9, 10, 11, 12 in the third, or you could recognize the pattern, 3 groups of 4, and understand through multiplication that 3 times 4 equals 12 apples total. This recognition of groups, of repeated addition, is the essence of multiplication. The word itself comes from Latin roots meaning to fold many times, to increase, to make multiple. When we multiply, we are seeing the same quantity repeated, appearing again and again, creating something larger through repetition. There is rhythm in multiplication, the rhythm of pattern repeating. 2 times 5 is 5 plus 5, 2 groups of 5. 3 times 5 is 5 plus 5 plus 5, 3 groups of 5. 4 times 5 continues the pattern, and so on, each building naturally on what came before. Ancient civilizations discovered multiplication through practical need. If 1 clay pot required 10 pieces of clay, how much clay was needed for 7 pots? Multiplication answered this question efficiently. If 1 field produced 20 bushels of grain, how much would 5 identical fields produce? Again, multiplication provided the answer without requiring laborious individual counting. The beauty of multiplication tables, those patterns of numbers that students often memorize, lies not in rote repetition, but in the deep symmetry they reveal. Notice that 2 times 3 equals 6, and 3 times 2 also equals 6. 4 times 7 and 7 times 4 both equal 28. This symmetry, this commutative property that also exists in addition, shows that multiplication is about relationship, and relationships can be viewed from either perspective. The grid of multiplication facts creates a beautiful landscape of number patterns. Look at the multiples of 2, the even numbers, marching upward in perfect intervals. 2, 4, 6, 8, 10, each one landing on a predictable, satisfying beat. The multiples of 5 create their own music, always ending in either 5 or 0, 5, 10, 15, 20, 25, 30. These patterns are not arbitrary, but arise from the deep structure of numbers themselves. Multiples of 9 have a particularly magical quality. 9, 18, 27, 36, 45, 54. If you add the digits of any multiple of 9, the result always reduces to 9. 9 is 9. 18 becomes 1 plus 8 equals 9. 27 becomes 2 plus 7 equals 9. This pattern continues infinitely, a hidden signature that 9 leaves on all its multiples. Such discoveries transform multiplication from mere calculation into something more like number mysticism, revealing that mathematics contains secrets and wonders waiting to be noticed. Division is perhaps the most philosophical of the basic operations, because division asks fundamental questions about fairness, about distribution, about what it means to share. When we divide, we are taking a whole and separating it into equal parts, ensuring that each part receives exactly the same amount. There is justice in division, equity, a deep human value made mathematical. Imagine 12 cookies that need to be shared equally among 4 friends. Division asks how many cookies each friend should receive so that no one has more or less than anyone else. 12 divided by 4 equals 3, and so each friend receives exactly 3 cookies. The division symbol itself, often written as a horizontal line with one dot above and one dot below, seems to represent this idea of separation into upper and lower, of splitting into parts. Division is the inverse of multiplication, just as subtraction is the inverse of addition. If 3 times 4 equals 12, then 12 divided by 4 equals 3, and 12 divided by 3 equals 4. These are not separate facts, but 3 ways of expressing the same relationship, the same truth viewed from different angles. Ancient peoples understood division through the practical necessity of distribution. If a harvest of 60 potatoes needed to be shared among 5 families, division determined that each family received 12 potatoes. If a length of rope measuring 30 units needed to be cut into 6 equal pieces, division revealed that each piece would measure 5 units. Division brings order to situations that might otherwise breed conflict or confusion. The language of division is revealing. We say that 12 divided by 4 equals 3, but we also say that 4 goes into 12 3 times, or that 12 contains 4 groups of 3. Each phrasing offers a slightly different perspective on the same operation. Division as separation, division as repeated subtraction, division as group formation, all these are valid ways to understand what is happening when we divide. Sometimes division produces neat whole number answers, and sometimes it does not. 12 divided by 5 does not result in a whole number, and this introduces us to remainders and eventually to fractions, concepts we will explore more deeply later. For now, simply notice that division invites us to think about what happens when quantities do not distribute perfectly, when reality is messier than our ideal patterns. This is not a failure of mathematics, but an expansion of it, a recognition that numbers can describe not only perfect situations, but also the imperfect, the incomplete, the in-between. There is something meditative about division practiced slowly and gently. Imagine taking 24 small objects, perhaps pebbles or buttons, and physically dividing them into equal groups. First, you might make 2 groups of 12. Then you might rearrange them into 3 groups of 8. Then 4 groups of 6. Each arrangement is valid. Each reveals a different factorization of 24, and together they show how a single number contains multiple relationships within itself. Our number system, the one we use every day without much thought, is built upon one of humanity's most elegant inventions, the concept of place value. Place value means that the position of a digit within a number determines its value, a simple idea with profound implications. Consider the number 347. The 7 sits in the ones place, representing simply 7 units. The 4 sits in the tens place, representing not 4, but 4 tens, which is 40. The 3 sits in the hundreds place, representing 3 hundreds, which is 300. Together, 300 plus 40 plus 7 gives us 347. This system allows us to represent any number, no matter how large, using only 10 symbols, the digits 0 through 9. The genius of place value is that it uses position to create value, so the same digit can mean different things depending on where it sits. The number 5 by itself means 5, but in the number 50, the 5 means 50 tens. In 500, the 5 means 5 hundreds. In 5,000, 5 thousands. The value multiplies by 10 each time we move one place to the left, creating a beautiful expanding pattern. Ancient civilizations used various number systems, some more cumbersome than others. The Romans used letters to represent numbers, which worked, but made arithmetic complicated. Adding XXXI and XLVII required careful manipulation of symbols. The Babylonians used a base 60 system, which survives today in how we measure time and angles. But the Hindu-Arabic place value system, developed over centuries and eventually spreading globally, offered unprecedented efficiency and flexibility. The inclusion of zero was crucial to making place value work properly. Zero is not nothing in the sense of absence, but rather a placeholder, a symbol that says this position is empty but still matters. In the number 305, the zero in the tens place indicates that there are no tens, but it holds that position so we know the 3 represents hundreds and the 5 represents ones. Without zero, we could not distinguish between 35 and 305 using place value alone. Moving to the right from the ones place, we encounter the decimal point and the realm of fractions expressed as decimals, though that too will be explored more fully later. For now, simply notice that the symmetry of the system, how each place to the left is 10 times larger and each place to the right is 10 times smaller. This regularity, this predictability, this elegant structure makes calculation possible and understanding accessible. Thinking about place value as you drift toward sleep, you might imagine numbers as towers of value, each floor precisely 10 times the value of the floor below. The ones place is the ground floor, solid and fundamental. The tens place is the first floor up, 10 times higher. The hundreds place is the second floor up, 10 times higher still. The building grows upward as far as needed, millions and billions and trillions, each floor maintaining its perfect proportion to the floors below and above.
Mathematics at its heart is the study of patterns, and nowhere are patterns more accessible and soothing than in simple number sequences. A pattern is simply any arrangement that repeats or follows a rule, and recognizing patterns is one of the most fundamental and satisfying activities the human mind performs. Consider the simplest pattern, counting by ones. 1, 2, 3, 4, 5. Each number is exactly one more than the number before. The pattern is so basic that we internalize it early and rarely think about it, yet it is the foundation upon which all other number patterns build. Counting by twos creates a different rhythm. 2, 4, 6, 8, 10, 12. These are the even numbers, numbers that can be divided evenly into two groups. Skip counting, as this is sometimes called, emphasizes every other number, creating a pattern of inclusion and exclusion. Counting by fives produces 5, 10, 15, 20, 25, a pattern particularly easy for humans because of our 5 fingers. These multiples of 5 always end in 5 or 0, a visual pattern that reinforces the numerical pattern. Similarly, counting by tens gives 10, 20, 30, 40, 50, 60, and so on, creating a pattern where only the tens place changes while the ones place remains 0. Patterns can also move backward, counting down from 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 is a pattern humans associate with anticipation and preparation, the countdown before a beginning. Each number is one less than the number before, a descending pattern that mirrors the ascending pattern of normal counting. Some patterns are more complex. Consider the sequence 1, 4, 7, 10, 13, 16. What is the pattern? Each number is 3 more than the number before. The difference between consecutive terms is consistently 3, making this an arithmetic sequence with a common difference of 3. Recognizing this pattern allows you to predict what comes next, 19, then 22, then 25, extending the sequence indefinitely. Other patterns multiply rather than add. In the sequence 2, 4, 8, 16, 32, each term is double the previous term. This is a geometric sequence where each number is multiplied by the same factor, in this case 2, to produce the next number. Such sequences grow rapidly, doubling, creating a swift expansion that has applications from bacterial growth to compound interest. The Fibonacci sequence is one of mathematics' most famous patterns, beginning with 0 and 1, then creating each subsequent number by adding the 2 previous numbers, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, expanding forever. This sequence appears remarkably often in nature, in the spiral of nautilus shells, the arrangement of pine cones, the branching of trees, the flowering of artichokes. That a simple numerical pattern should manifest in living organisms across the biological world suggests deep connections between mathematics and the structure of reality itself. Geometry, the mathematics of shape and space, offers a different kind of peaceful contemplation than arithmetic. Where numbers are abstract, shapes are visual and tangible. Where calculation requires sequential steps, understanding shapes often comes in moments of recognition, instant and complete. The most basic shape is the circle, a collection of points all equally distant from a center point. The circle has no beginning and no end, no corners or edges, just smooth, continuous curve. It is symmetry perfected, looking identical from any angle. Ancient peoples saw circles in the sun and moon, in ripples on water, in the pupils of eyes. The circle represents wholeness, completion, infinity, the eternal return. There is deep peace in the circle's perfection. A triangle is a shape of 3 sides and 3 corners, called vertices. The triangle is the simplest polygon, the first shape that encloses space using straight lines. With only 3 sides, the triangle has a rigid stability. Unlike shapes with 4 or more sides that can deform while keeping their side lengths, a triangle's shape is completely determined by its side lengths. This makes triangles fundamental in construction and engineering. They do not wobble or collapse. Ancient architects understood this, using triangular supports and triangular roof structures to create stability. Different types of triangles have different characters. An equilateral triangle has all 3 sides of equal length, creating maximum symmetry, with all 3 angles also equal. An isosceles triangle has 2 equal sides and 2 equal angles, a kind of bilateral symmetry like a human face. A scalene triangle has no equal sides and no equal angles, complete asymmetry, each side and angle unique. Right triangles with one 90-degree angle form the basis of trigonometry and have special importance in mathematics, but that is a topic for deeper exploration than tonight requires. Squares and rectangles bring us to 4-sided figures, quadrilaterals. A square has 4 equal sides and 4 right angles, embodying regularity and balance. Squares tile perfectly, covering a plane without gaps or overlaps, which is why floor tiles in city blocks are often square. A rectangle is like a stretched or compressed square, still having 4 right angles, but with 2 sides longer than the other 2. Rectangles also tile perfectly and appear everywhere in human design, from books to buildings to screens. The pentagon has 5 sides, the hexagon has 6, the heptagon 7, the octagon 8, and so the sequence continues. As the number of sides increases, the polygon begins to approximate a circle, the angles becoming more numerous and each one less sharp. A polygon with 1,000 sides would look nearly circular to the human eye, though mathematically it remains distinct, still composed of straight-line segments rather than a continuous curve. Hexagons have special properties that make them appear frequently in nature. Beehives construct their honeycomb cells as hexagons because this shape tiles perfectly and uses the minimum amount of wax to create the maximum storage space. The efficiency of the hexagonal tiling is a mathematical optimum, and somehow, through evolutionary trial or instinctive genius, bees discovered this truth.
An angle is formed when 2 lines or rays meet at a point, and understanding angles is understanding rotation, turning, the geometry of change in direction. Angles are measured in degrees, a system inherited from ancient Babylonian mathematics that divided the circle into 360 parts. Why 360? Because this number has many divisors, making calculations easier in an age before calculators. 360 can be evenly divided by 2, 3, 4, 5, 6, 8, 9, 10, 12, and more, giving it remarkable flexibility. A full rotation, turning completely around to face the same direction again, encompasses 360 degrees. Half a rotation, turning to face the opposite direction, is 180 degrees.
A quarter rotation, turning 90 degrees, creates a right angle, the angle found in squares and rectangles, the angle between horizontal floor and vertical wall, between the cardinal directions north and east, south and west. There is something perfectly natural and satisfying about the right angle, the 90-degree turn that feels complete and stable. An angle smaller than 90 degrees is called acute, meaning sharp or pointed. These angles are less than a right angle, creating sharper corners, more pointed shapes. An angle larger than 90 degrees but less than 180 degrees is called obtuse, meaning blunt or dull. These angles are wider, more open, less pointed. When two lines meet to form a straight line, the angle is exactly 180 degrees, called a straight angle, though it barely looks like an angle at all since the two rays point in opposite directions along a single line. Angles appear everywhere in the visual world. The hands of a clock form different angles as time passes. At 3 o'clock, the hour and minute hands form a right angle. At 6 o'clock, they form a straight angle. At 1 o'clock, they form a 30-degree angle, acute and narrow. The constant movement of clock hands through changing angles is a visible representation of time's passage, geometry and chronology united. Tree branches grow from trunks at various angles, some acute, some obtuse, creating the distinctive silhouettes that allow us to identify species from a distance. The angle at which a bird's wings meet its body changes with different flying behaviors. Narrow angles for swift diving, wider angles for soaring and gliding. Architecture relies fundamentally on angles. Roofs meet walls at specific angles designed to shed rain and snow. Stairs rise at angles steep enough to save space, but shallow enough to climb comfortably. Ramps, designed for accessibility, must maintain angles gentle enough for wheelchairs while still making vertical progress. The angles in these structures are not decorative but functional, mathematical decisions with practical consequences. Perimeter is simply the distance around the edge of a shape, the length you would walk if you traveled around its border and returned to your starting point. For shapes with straight sides, calculating perimeter means adding the lengths of all the sides together. A rectangle with length 10 and width 6 has a perimeter of 10 plus 6 plus 10 plus 6, which equals 32. You count each side, walking mathematically around the entire edge. For a square, since all four sides are equal, perimeter is simply 4 times the length of one side. A square with sides of 7 has a perimeter of 4 times 7, which equals 28. The symmetry of the square makes the calculation particularly simple and elegant. Any polygon's perimeter is found the same way, by adding all side lengths. A triangle with sides of 3, 4, and 5 has a perimeter of 3 plus 4 plus 5, which equals 12. A pentagon with each side measuring 8 has a perimeter of 5 times 8, which equals 40. The process is straightforward, patient, requiring only addition and awareness of the shape's structure. The perimeter of a circle, interestingly, is called the circumference, a special term for a special shape. The circumference relates to the circle's diameter, the distance across its widest point, through a famous constant called pi. The circumference equals pi times the diameter, or equivalently, 2 times pi times the radius. This relationship between the circumference and diameter is always the same ratio, approximately 3.14, no matter how large or small the circle. This consistency, this universal proportion found in every circle ever drawn, is one of mathematics' most beautiful and mysterious truths. Thinking about perimeter has a meditative quality because it asks you to trace boundaries, to follow edges with your mind's eye. Imagine slowly walking around the edge of a large square field, counting your steps, feeling the right angle turns at each corner. The perimeter is your journey, the total distance you travel before returning to your start. Or imagine running your finger along the rim of a circular plate, the smooth journey with no corners, no interruptions, just continuous progress that eventually returns to its beginning. Perimeter connects mathematics to physical experience, to the act of surrounding and closing, defining borders. Fences have perimeters, as do gardens, rooms, lakes, continents. Any region with a defined edge has a perimeter, even if measuring it proves difficult. The coastline of an island has a perimeter, though the irregular curves and inlets make calculation complex. The frame around a painting creates a rectangular perimeter that separates art from wall. Perimeter is about boundaries, about where one thing ends and another begins. While perimeter measures the edge, area measures the space inside, the two-dimensional region enclosed by the boundary. Area is about coverage, about how much surface exists within the borders. For rectangles, area is found by multiplying length times width. A rectangle 10 units long and 6 units wide has an area of 10 times 6, which equals 60 square units. Square units, whether square inches, square feet, square meters, are the standard measurement because they represent the small squares that tile the region. Imagine laying down 1 unit squares to cover the rectangle completely. You would fit 6 squares along the width and 10 squares along the length, creating a grid of 60 squares total. This is area, the count of unit squares needed to tile the space. For a square, since length and width are equal, area is the side length multiplied by itself, which we call squaring. A square with sides of 7 has an area of 7 times 7, which equals 49 square units. The word squared as a mathematical operation literally comes from this geometric fact. When we say 7 squared, we are imagining a square with sides of 7 and calculating its area. Triangles require a different formula because their shape is different. The area of a triangle is 1/2 times base times height. This makes sense if you imagine 2 identical right triangles fitting together to form a rectangle. The rectangle's area would be base times height, and since the triangle is exactly half the rectangle, we multiply by 1/2. This relationship reveals how different formulas are not arbitrary, but emerge from the logical structure of shapes themselves. Circles, again, require the special constant pi. The area of a circle is pi times the radius squared. This formula gives us the number of square units needed to cover the circular region. Because circles have curved edges, they cannot be perfectly tiled by squares, but the formula gives the equivalent area, the amount of space enclosed within the circumference. Understanding area is understanding capacity, coverage, extent. Paint is sold by coverage area because what matters is how much wall surface a gallon can cover. Land is bought and sold by area, acres and hectares measuring how much ground is owned. Carpet is purchased by area because you need enough material to cover your floor completely. Area is practical and tangible, a measurement of resources needed and space possessed. In agriculture, field area determines how many crops can be planted. In architecture, floor area determines how many rooms can fit in a building. In nature, leaf area determines how much sunlight a plant can capture for photosynthesis. Area is a fundamental measure of capacity, of potential, of what can fit within given boundaries. Contemplating area while relaxing, you might imagine various shapes slowly filling with color, the rectangle flooding with blue from one corner, the square glowing evenly with yellow, the circle rippling outward with green from its center, each shape holding its area of color within its perimeter boundary. Fractions emerge naturally when we need to describe parts of wholes, when something is divided into equal pieces and we want to specify one or more of those pieces. If a pie is cut into 8 equal slices and you take 3 slices, you have 3/8 of the pie. The fraction 3/8 tells a complete story. The bottom number, called the denominator, says the whole was divided into 8 equal parts, and the top number, called the numerator, says you have 3 of those parts. The beauty of fractions is their precision. They allow us to specify portions exactly, not approximately. 1/2 is exactly one of 2 equal parts, perfectly precise. 1/3 is exactly one of 3 equal parts. 1/4, one of 4 equal parts. These simple fractions appear constantly in daily life. Recipes call for 1/2 cup of flour, 1/3 teaspoon of salt, 1/4 pound of butter. Time divides into halves and quarters. Half an hour is 30 minutes, 1/4 of an hour is 15 minutes. Money divides similarly. Half a dollar is 50 cents, 1/4 of a dollar is 25 cents. Fractions with the same value but different appearances are called equivalent fractions, and understanding equivalence is key to understanding fractions deeply. 1/2 and 2/4 are equivalent, both representing the same amount. If you cut a pie into 2 equal pieces and take 1, or cut it into 4 equal pieces and take 2, you have eaten the same amount of pie. Similarly, 2/3 and 4/6 are equivalent, 3/4 and 6/8 are equivalent, always in the same proportion. The process of simplifying fractions means finding the equivalent fraction with the smallest possible numbers. 6/8 can be simplified to 3/4 by dividing both the numerator and denominator by 2. 10/15 simplifies to 2/3 by dividing both numbers by 5. This simplification does not change the value, only the way we express it, like choosing simpler words to say the same thing. Adding fractions with the same denominator is straightforward and peaceful. 2/8 plus 3/8 equals 5/8. The denominator stays the same because the size of the pieces hasn't changed, and we simply count how many pieces we have total. 3/10 plus 4/10 equals 7/10. 1/5 plus 2/5 equals 3/5. When denominators match, addition is simply adding the numerators. When denominators differ, we need to find equivalent fractions with common denominators before adding, but that is a complexity beyond tonight's gentle pace. For now, simply appreciate that fractions allow mathematics to describe not only whole numbers, but any portion of a whole, expanding our ability to measure, compare, and understand the world with precision and elegance.
Decimals extend the place value system beyond whole numbers into the realm of parts and fractions, using the same elegant structure that makes whole numbers so manageable. The decimal point, a small dot, marks the boundary between the whole number part and the fractional part. To the right of the decimal point, each position represents a fraction with a denominator that is a power of 10. The first position right of the decimal is the tenths place, representing fractions with denominator 10. The second position is the hundredths place, representing fractions with denominator 100. The third position is the thousandths place, denominator 1000, and so on, each position 10 times smaller than the position to its left. The number 3.5 means 3 and 5/10, which could also be written as the mixed number 3 and 1/2, since 5/10 equals 1/2. The number 0.25 means 0 and 25/100, which simplifies to 1/4. Decimals and fractions are two ways of expressing the same values, decimal notation often being more convenient for calculation, while fractions sometimes make relationships clearer. Money is typically expressed in decimal form because our currency divides dollars into 100 cents. The amount $3.50 is written as $3.50, the 5 in the tenths place representing 5 dimes, the 0 in the hundredths place representing 0 additional pennies. This decimal representation makes addition and subtraction of money amounts use the same algorithms as whole number arithmetic, a significant practical advantage. Decimal fractions less than 1 describe measurements that fall between 0 and 1. An athlete might run a race in 9.58 seconds, meaning 9 seconds and 58 hundredths of a second. A measurement might be 0.75 meters, meaning 75 hundredths of a meter, which equals 3/4 of a meter. The precision of decimal notation allows us to specify quantities as exactly as our measuring tools permit. Adding and subtracting decimals follows the same process as with whole numbers, provided we keep the decimal points aligned. Adding 2.3 and 1.5 means adding 2 and 1 to get 3, then adding 3/10 and 5/10 to get 8/10, giving an answer of 3.8. The process is peaceful and systematic, each place value adding with its corresponding place value, just as with whole numbers.
Multiplying decimals involves temporarily ignoring the decimal point, multiplying as if the numbers were whole numbers, then placing the decimal point in the answer based on the total number of decimal places in the factors. This sounds complicated, but becomes natural with practice. The logic ensures that the answer has the right scale, the right magnitude, neither too large nor too small. Decimals appear everywhere in science and measurement because the metric system, used by most of the world, is built on powers of 10, perfectly matching decimal notation. A distance might be 5.2 kilometers, a mass might be 0.75 kilograms, a volume might be 1.3 liters. The decimal point enables precise communication of measured quantities in a notation that aligns perfectly with place value. An equation is a mathematical sentence stating that two expressions are equal, connected by an equal sign. The simplest equations involve an unknown value, often represented by a letter like x, that we need to find. These unknowns are called variables because their values can vary depending on the equation. Solving an equation means finding the value of the variable that makes the equation true. Consider the equation x plus 3 equals 7. This asks, what number plus 3 gives 7? The answer is 4, because 4 plus 3 equals 7. We can also solve this more formally by subtracting 3 from both sides of the equation, preserving the equality. If x plus 3 equals 7, then x plus 3 minus 3 equals 7 minus 3, which simplifies to x equals 4. The process is logical and peaceful, each step maintaining balance. The equal sign in an equation acts like a balance point on a scale. Whatever is on the left must equal whatever is on the right. If we add something to one side, we must add the same thing to the other side to maintain balance. If we multiply one side by something, we must multiply the other side by the same thing. This principle of maintaining equality guides all equation solving. Another example, 2 times x equals 10. This asks, what number times 2 gives 10? The answer is 5, because 2 times 5 equals 10. Formally, we divide both sides by 2. If 2 times x equals 10, then 2 times x divided by 2 equals 10 divided by 2, which simplifies to x equals 5. The operation that undoes multiplication is division, just as the operation that undoes addition is subtraction. Equations can involve multiple operations. Consider 3 times x plus 4 equals 13. To solve this, we first isolate the term containing x by subtracting 4 from both sides, giving 3 times x equals 9. Then we divide both sides by 3, giving x equals 3. We can verify this answer by substituting 3 back into the original equation. 3 times 3 plus 4 equals 9 plus 4 equals 13. The equation is satisfied, confirming our solution. Variables are not mysterious or abstract once you understand that they simply represent numbers we don't yet know. In the equation x plus 5 equals 12, x is just a placeholder for whatever number, when added to 5, gives 12. That number is 7, and so x equals 7. The variable is a blank to be filled, a question to be answered, a mystery to be solved through logical steps. Equations appear throughout mathematics and science because they express relationships. If distance equals rate times time, then this equation relates 3 quantities, and knowing any 2 allows us to find the third. If temperature in Celsius relates to temperature in Fahrenheit through the equation F equals 9/5 times C plus 32, then we can convert between the two scales using algebraic manipulation. Equations are tools for encoding knowledge and enabling calculation. Negative numbers extend the number line in the opposite direction from positive numbers, creating a complete and symmetric system. 0 sits at the center, neither positive nor negative, the boundary between the two realms. Positive numbers extend to the right, 1, 2, 3, growing larger without limit. Negative numbers extend to the left, -1, -2, -3, growing smaller without limit, though by smaller we mean further from 0 in the negative direction. Understanding negative numbers often begins with temperature. If 0 degrees is the freezing point of water, then temperatures below freezing are described with negative numbers. Negative 10 degrees means 10 degrees below 0, colder than freezing. Negative 20 degrees is colder still. In this context, negative numbers describe something tangible and real, the intensity of cold, the absence of heat. Money provides another intuitive context. If your bank account balance is 0, you have no money. If you have $50, your balance is positive 50. But if you overdraw your account and owe the bank $30, your balance is negative 30. The negative number represents debt, what you owe rather than what you have. As you deposit money, the balance increases, moving from negative through 0 into positive, from debt through balance to surplus. The number line is a powerful visual tool for understanding negative numbers. Imagine a horizontal line with 0 marked at the center. Positive numbers are marked to the right at regular intervals, 1, 2, 3, and so on. Negative numbers are marked to the left, -1, -2, -3, and so on. This representation makes clear that negative numbers are not separate from positive numbers, but part of one continuous system, the integers, extending infinitely in both directions. Adding a negative number is equivalent to subtracting its positive counterpart. 5 plus -3 equals 5 minus 3, which equals 2. If you start at 5 on the number line and add -3, you move 3 units to the left, landing on 2. Subtracting a negative number is equivalent to adding its positive counterpart. 7 minus -2 equals 7 plus 2, which equals 9. Subtracting a negative means moving left by a leftward number, which results in moving right back towards the positive. Multiplying with negatives follows rules that seem strange at first, but are logically consistent. A positive times a positive is positive. 3 times 4 equals 12. A positive times a negative is negative. -3 times -4 equals -12. Multiplying by a negative flips the sign. A negative times a positive is negative. -3 times 4 equals -12. But a negative times a negative is positive. -3 times -4 equals positive 12. Two sign flips result in returning to positive. These rules ensure that all the algebraic properties we rely on remain consistent across the entire number system. Negative numbers are not strange or unnatural once we see them as extensions of the number system, tools for describing situations where quantities can move in two opposite directions, gains and losses, credits and debts, temperatures above and below a reference point, elevations above and below sea level. 0 is perhaps the most philosophically interesting number because it represents both nothing and something. As a quantity, 0 means none, the absence of amount. If you have 0 apples, you have no apples. But as a number in our mathematical system, 0 is far from nothing. It is the additive identity, the boundary between positive and negative, the origin point from which all counting begins. In the place value system, 0 serves as a placeholder, allowing us to distinguish between numbers like 30 and 300. Without 0, writing numbers would be ambiguous and confusing. The invention of 0 as a written symbol was a major mathematical breakthrough, not obvious to ancient civilizations, some of whom managed complex calculations without ever representing 0 explicitly. 0 has unique properties in arithmetic. Adding 0 to any number leaves that number unchanged. 5 plus 0 equals 5. -3 plus 0 equals -3. 0 plus 0 equals 0. This is why 0 is called the additive identity. It preserves identity under addition. Multiplying any number by 0 gives 0. 7 times 0 equals 0. -15 times 0 equals 0. 1,000,000 times 0 equals 0. Multiplication by 0 annihilates, reducing everything to nothing. This property seems simple, but has profound implications throughout mathematics. Division by 0, however, is undefined, not allowed, creating a boundary that mathematics cannot cross. Why? Because division asks, what do we multiply the divisor by to get the dividend? If we try to calculate 5 divided by 0, we are asking, what times 0 equals 5? But nothing times 0 equals 5. Every number times 0 equals 0. The question has no answer, and so we say division by 0 is undefined, a limitation we must respect. 0 as a concept connects to ideas of neutrality, balance, nothingness, origin. In temperature, 0 degrees Celsius is the freezing point of water, a meaningful reference point. In accounting, 0 balance means no debt and no surplus, perfect equilibrium. In physics, 0 velocity means no motion, 0 acceleration means constant velocity, 0 force means equilibrium. 0 marks boundaries and beginnings. Year 0 in a timeline, though often omitted in practice, would mark the boundary between negative and positive dates. Ground zero means the starting point, the origin, the place from which measurement begins. 0 elevation is sea level, the reference from which we measure mountains and ocean depths. Contemplating 0 as you drift towards sleep, you might think of it as silence in music, the rests between notes that give structure and meaning to sound. Without silence, music would be continuous noise. 0 is the mathematical silence, the nothing that makes something meaningful, the absence that defines presence. Probability is the mathematics of likelihood, of chance, of how often we expect events to occur. It ranges from 0 to 1, where 0 means impossible, 1 means certain, and values in between represent varying degrees of likelihood. Understanding probability helps us think clearly about uncertainty, about the randomness that permeates life. Consider flipping a coin. There are two possible outcomes, heads or tails, and if the coin is fair, each outcome is equally likely. The probability of getting heads is 1 out of 2, which we write as 1/2 or 0.5 or 50%. These are all equivalent ways of expressing the same likelihood. Each time you flip, you have a 50-50 chance of heads. Rolling a standard 6-sided die offers 6 possible outcomes, the numbers 1 through 6. If the die is fair, each outcome is equally likely. The probability of rolling a 3 is 1 out of 6, approximately 0.166, or about 16.7%. The probability of rolling an even number, 2, 4, or 6, is 3 out of 6, which simplifies to 1/2, because 3 of the 6 outcomes are even. Probability is calculated as the number of favorable outcomes divided by the total number of possible outcomes, assuming all outcomes are equally likely. If a bag contains 5 red marbles and 3 blue marbles, the probability of drawing a red marble at random is 5 out of 8, because 5 of the 8 marbles are red. The probability of drawing a blue marble is 3 out of 8. Notice that these probabilities sum to 1/8, which equals 1, which equals certainty. Something must happen. Either you draw red or you draw blue, and so the probabilities of all possible outcomes always sum to 1. Independent events are those where one outcome does not affect another. Flipping a coin twice involves 2 independent events. The result of the first flip does not change the probabilities for the second flip. If you flip heads the first time, the second flip still has a 50% chance of heads and 50% chance of tails. The coin has no memory, no tendency to balance out. Each flip is fresh, independent, its probabilities unchanged by history. Calculating the probability that 2 independent events both occur involves multiplication. The probability of flipping heads twice in a row is 1/2 times 1/2, which equals 1/4, or 0.25, or 25%. The probability of rolling a 6 and then flipping heads is 1/6 times 1/2, which equals 1/12, approximately 0.083, or about 8.3%. Probability helps us understand games of chance, risk in decision-making, patterns in random data. Weather forecasts express probability. A 70% chance of rain means in similar conditions, rain occurs 7 times out of 10. Medical tests report probabilities, the likelihood that a positive test indicates disease, the likelihood that treatment will succeed. Insurance premiums are calculated based on probabilities, the likelihood of accidents, illness, disaster. Statistics is the mathematics of data, of collecting, analyzing, and interpreting information. When we have a set of numbers, measures of center help us understand the typical or average value, the number that best represents the entire set. The 3 most common measures of center are mean, median, and mode, each offering a different perspective on what is typical. The mean, often called the average, is found by adding all the values and dividing by how many values there are. If 5 students score 80, 70, 90, 60, and 85 on a test, the mean is the sum of these scores divided by 5. 80 plus 70 plus 90 plus 60 plus 85 equals 385. 385 divided by 5 equals 77. The mean score is 77. This single number summarizes the performance of all 5 students. The median is the middle value when the data is arranged in order. Using the same test scores, we first arrange them from lowest to highest: 60, 70, 80, 85, 90. The middle value is 80, and so the median is 80. If there are an even number of values, the median is the mean of the 2 middle values. The median is resistant to extreme values, unlike the mean. If one student scored 10 instead of 60, the mean would drop significantly, but the median might remain the same, still pointing to the middle of the data. The mode is the value that appears most frequently. In our test score example, 80 appears twice while all other scores appear once, so the mode is 80. Some datasets have no mode if all values appear equally often, and some have multiple modes if several values tie for most frequent. The mode identifies the most common outcome, which can be useful when that information is meaningful. These 3 measures can give different results, and understanding why reveals important information about the data's distribution. If mean, median, and mode are close together, the data is probably symmetric, distributed evenly around the center. If they differ substantially, the data is probably skewed, stretched out more on one side than the other. Considering a few examples clarifies how these measures behave. If 7 people have the following amounts of money: $5, $5, $10, $10, $10, $15, and $15, the mode is $10 because it appears most often. The median is $10 because it is the middle value when arranged in order. The mean is $70 divided by 7, which is $10. All 3 measures agree, suggesting a balanced, symmetric distribution. But if the amounts were 5, 5, 5, 10, 10, 15, and 100, the mode is 5, the median is 10, and the mean is 150 divided by 7, approximately 21.4. The mean is pulled upward by the 100, an outlier much larger than the others. The median and mode give a better sense of the typical amount in this case. Graphs and charts translate numbers into visual form, making patterns and relationships immediately apparent to the eye. Different types of graphs suit different kinds of data, each offering unique insights. A bar graph uses rectangular bars to represent quantities, the height or length of each bar proportional to the value it represents. If a class survey finds that 10 students prefer pizza, 7 prefer burgers, and 3 prefer salad, a bar graph would show 3 bars, the first reaching to 10, the second to 7, the third to 3. The visual comparison is immediate. Bar graphs are excellent for comparing discrete categories. A line graph connects points with lines to show how something changes over time, or in relation to another continuous variable. If you record temperature at noon each day for a week, you might plot the 7 data points and connect them with line segments, creating a line graph. Rising lines indicate increasing temperature, falling lines indicate decreasing temperature, horizontal lines indicate steady temperature. The line graph reveals trends and patterns in the progression. A pie chart divides a circle into wedges, each wedge representing a portion of a whole. If a budget allocates 40% to housing, 30% to food, 20% to transportation, and 10% to entertainment, a pie chart would divide the circle into wedges of these proportions. The visual representation makes clear how the whole is divided, which portions are large, which small. Pie charts are ideal for showing parts of a whole, percentages that sum to 100. A scatter plot uses dots to represent pairs of values, showing whether relationships exist between two variables. If you plot hours studied versus test scores for 20 students, each student is a dot, positioned horizontally based on hours studied and vertically based on test score. If dots trend upward from left to right, more study hours correlate with higher scores. If dots show no pattern, the variables may be unrelated. Scatter plots reveal correlation, relationship, pattern, or lack thereof. Reading a graph requires understanding its axes, the horizontal and vertical reference lines from which measurements are made. The horizontal axis, often called the x-axis, typically represents the independent variable or categories. The vertical axis, the y-axis, typically represents the dependent variable or measurements. Scale matters. If the vertical axis begins at 0, differences appear proportional to reality. If the axis begins at a higher number, differences appear exaggerated, potentially misleading. Critical reading of graphs includes checking scales, labels, and sources. Graphs are powerful tools for communication because they engage visual processing, allowing humans to perceive relationships that would be difficult to extract from tables of numbers. A well-designed graph tells a story, guides the eye, reveals truth. Graphs appear everywhere, in news articles explaining trends, in scientific papers presenting data, in business presentations comparing performance, in educational materials teaching concepts.
When a mathematical expression involves multiple operations, the order in which we perform them matters tremendously. Consider 5 plus 3 times 2. If we add first, we get 8, then multiply by 2 to get 16. If we multiply first, we get 6, then add 5 to get 11. These different answers arise from different orders, and mathematics requires agreement on one standard order to ensure everyone gets the same answer. The agreed-upon order is remembered by the acronym PEMDAS, which stands for parentheses, exponents, multiplication and division from left to right, addition and subtraction from left to right. Some people remember this as, "Please excuse my dear Aunt Sally," a mnemonic that has helped countless students internalize the sequence. Parentheses have highest priority. Any calculation inside parentheses must be completed before operations outside parentheses. In the expression 4 times open parenthesis 7 minus 3 close parenthesis, we first calculate 7 minus 3 to get 4, then multiply 4 times 4 to get 16. The parentheses create a subcalculation that takes precedence. Exponents come next, representing repeated multiplication. We will explore exponents more fully soon, but for now, know that they are evaluated after parentheses but before multiplication, division, addition, and subtraction. Multiplication and division have equal priority and are performed from left to right as they appear. In the expression 20 divided by 4 times 2, we work left to right, first dividing 20 by 4 to get 5, then multiplying 5 by 2 to get 10. If the expression were 20 divided by open parenthesis 4 times 2, close parenthesis, we would first calculate 4 times 2 to get 8, then divide 20 by 8 to get 2.5. The parentheses change the order and thus change the answer. Addition and subtraction also have equal priority and are performed from left to right. In the expression 15 minus 6 plus 2, we work left to right, first subtracting 6 from 15 to get 9, then adding 2 to get 11. Understanding order of operations allows us to write complex calculations unambiguously. The expression 3 plus 4 times 5 means 3 plus 20, which equals 23, because multiplication happens before addition.
If we wanted the addition to happen first, we would write open parenthesis 3 plus 4 close parenthesis times 5, which equals 7 times 5, which equals 35. Order of operations is not arbitrary, but necessary for clear communication. Without agreed order, every expression would be ambiguous, requiring additional context or explanation. With order of operations, a single expression has one definite meaning that everyone can calculate consistently. This shared understanding is fundamental to mathematics as a language. An exponent indicates repeated multiplication, a shorthand for multiplying a number by itself multiple times. When we write 2 to the power of 3, written with a small raised 3 after the 2, we mean 2 times 2 times 2, which equals 8. The bottom number is the base, the number being multiplied. The raised number is the exponent, telling how many times the base appears as a factor. 5 to the power of 2 means 5 times 5, which equals 25. 4 to the power of 3 means 4 times 4 times 4, which equals 64. The exponent counts the factors. Saying to the power of is formal language, but we also say squared for exponent 2 and cubed for exponent 3. 7 squared means 7 to the power of 2, which equals 49. 2 cubed means 2 to the power of 3, which equals 8. These special terms connect to geometry. Squaring relates to the area of a square, cubing to the volume of a cube. Exponents grow rapidly. 2 to the power of 5 is 32. 2 to the power of 10 is 1024. Exponential growth, where quantities repeatedly multiply, leads to surprisingly large numbers quickly. This pattern appears in compound interest, population growth, viral spreading, any situation where growth feeds on itself. Any number to the power of 1 equals itself. 9 to the power of 1 equals 9. Negative 17 to the power of 1 equals negative 17. The exponent 1 means the base appears once with no multiplication beyond the single factor. Any non-zero number to the power of 0 equals 1, a fact that seems strange but makes sense within the logical structure of exponents. Why does 5 to the power of 0 equal 1? Because exponential patterns require it. 5 to the power of 3 is 125. 5 to the power of 2 is 25, which is 125 divided by 5. 5 to the power of 1 is 5, which is 25 divided by 5. Following this pattern, 5 to the power of 0 should be 5 divided by 5, which equals 1. Exponents can also be negative, indicating division rather than multiplication. 2 to the power of negative 3 means 1 divided by 2 to the power of 3, which is 1 divided by 8, which equals 0.125. Negative exponents create fractions, reciprocals of the corresponding positive exponent. The laws of exponents describe how to combine exponential expressions. When multiplying same bases, add exponents. 2 to the power of 3 times 2 to the power of 4 equals 2 to the power of 7, because you have a total of 7 factors of 2. When dividing same bases, subtract exponents. 5 to the power of 6 divided by 5 to the power of 2 equals 5 to the power of 4, because you cancel 2 factors of 5 from numerator and denominator. When raising a power to a power, multiply exponents. 2 to the power of 3, all raised to the power of 2, equals 2 to the power of 6, because you have 2 groups of 3 factors. If squaring a number means multiplying it by itself, then finding a square root means asking what number, when squared, gives a particular result. The square root of 9 is 3, because 3 squared equals 9. The square root of 16 is 4, because 4 squared is 16. The square root of 25 is 5, 25 being 5 squared. The square root symbol looks like a check mark with a horizontal line extending to the right, covering the number whose root we seek. This symbol asks the question, what number was squared to produce this value? Not all square roots are whole numbers. The square root of 10 is not a whole number, but approximately 3.162, a number that when multiplied by itself gives very close to 10. The square root of 2 is approximately 1.414, an irrational number whose decimal expansion never terminates or repeats. These non-whole square roots are no less real or valid than whole number roots, simply less tidy. Perfect squares are numbers that have whole number square roots: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. These are the first 10 perfect squares, the results of squaring 1 through 10. Recognizing perfect squares helps with estimating roots. If you need the square root of 50, you know it falls between 7 and 8 because 49 is 7 squared and 64 is 8 squared. Square roots appear in geometry when working with the Pythagorean Theorem, when calculating distances, when determining side lengths from areas. If a square has area 36, its side length is the square root of 36, which is 6. If a square has area 40, its side length is the square root of 40, approximately 6.325. Cube roots extend the idea to 3 dimensions. The cube root of 8 is 2, because 2 cubed equals 8. The cube root of 27 is 3, because 3 cubed equals 27. The cube root asks what number multiplied by itself 3 times produces the given value. Higher roots follow the same pattern: fourth roots asking what to the power of 4, fifth roots asking what to the power of 5. Roots and exponents are inverse operations, opposite processes that undo each other. Squaring and taking square roots are inverses. If you square 3 to get 9, then take the square root of 9, you return to 3. If you cube 2 to get 8, then take the cube root of 8, you return to 2. This inverse relationship is like the relationship between addition and subtraction, multiplication and division, a fundamental symmetry in mathematical operations. Understanding square roots brings a sense of completion, showing that every operation has a counterpart, that mathematics is balanced and self-consistent. For every question mathematics asks, it provides tools for finding answers. Returning to multiplication with fresh eyes, we can appreciate the rich patterns hidden within multiplication tables, patterns that reveal deep structure and how numbers relate. The multiplication table is typically organized as a grid, with one factor along the top, another factor along the left side, and their product in the intersecting cell. This grid is symmetric across the diagonal, reflecting the commutative property that 3 times 5 equals 5 times 3. The diagonal itself, where a number multiplies by itself, contains the perfect squares: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. These numbers form a sequence with increasing gaps between consecutive terms, the differences being odd numbers: 3, 5, 7, 9, growing steadily. Looking at individual rows or columns reveals the sequence of multiples for that number. The row for 3 contains 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Each number 3 more than the previous. Arithmetic progression with common difference 3. Every row is an arithmetic sequence, the common difference being the number whose multiples are listed. The 5s row has particularly pleasing rhythm: 5, 10, 15, 20, 25, 30, alternating between numbers ending in 5 and numbers ending in 0. This pattern makes the 5's multiplication facts among the easiest to remember and use. The 2s row contains all even numbers, doubling creating the most basic pattern. The 9s row has the digit sum property mentioned earlier, where the digits of each product sum to 9. But 9s also have another pattern. The 10's digit increases by 1 each step, while the 1's digit decreases by 1. 9, 18, 1 and 8, 27, 2 and 7, 36, 3 and 6, 45, 4 and 5, a perfect symmetry in the digit structure. The 11's row, when multiplied by single digits, produces a delightful pattern: 11, 22, 33, 44, 55, 66, 77, 88, 99. Each product a repeating digit, the numbers simply written twice. This makes 11 multiplication particularly memorable. Multiples of 10 are easy because they simply add a 0 to the other factor. 10 times 4 is 40, 10 times 7 is 70. This reflects the place value system, where multiplying by 10 shifts everything one place to the left, the ones becoming tens, the tens becoming hundreds. Exploring these patterns is meditative because it transforms multiplication from memorized facts into discovered truths. Each pattern is a small revelation, a glimpse into the architecture of numbers. Time is measured in units that don't follow the decimal system most other measurements use. 60 seconds make 1 minute, 60 minutes make 1 hour, 24 hours make 1 day, 7 days make 1 week. These irregular conversions reflect historical decisions and astronomical realities, the day being Earth's rotation period, the year being Earth's orbit around the Sun. Calculating with time requires adjusting for these varied units. Adding 2 hours and 45 minutes to 1 hour and 30 minutes requires careful attention. The hours add directly. 2 plus 1 equals 3. The minutes add directly. 45 plus 30 equals 75. But 75 minutes exceeds 60, which means it contains 1 hour and 15 minutes. We add this hour to our 3 hours, reaching 4 hours and 15 minutes total. The process is logical, but requires conversion awareness. Subtracting time follows similar logic. 4 hours and 20 minutes minus 1 hour and 50 minutes requires borrowing when the minutes are insufficient. We cannot subtract 50 from 20, so we borrow 1 hour, converting it to 60 minutes, turning 4 hours and 20 minutes into 3 hours and 80 minutes. Now we can subtract. 80 minus 50 is 30, and 3 minus 1 is 2, giving 2 hours and 30 minutes. Time calculations appear constantly in daily life. If a movie starts at 7:15 and runs for 2 hours and 25 minutes, when does it end? Add the durations, 7 hours 15 minutes plus 2 hours 25 minutes. 7 plus 2 is 9, 15 plus 25 is 40 minutes, so the movie ends at 9:40, or 9:40 p.m. if we're using 12-hour clock notation. The 12-hour clock divides the day into two 12-hour periods, AM for morning hours and PM for afternoon and evening hours. The 24-hour clock, used in many countries and contexts, runs from 0 hours to 23 hours, eliminating the AM-PM distinction. 1400 hours in 24-hour notation equals 2 p.m. in 12-hour notation. 14 minus 12 equals 2. Converting between notations is straightforward once understood. Elapsed time calculations ask how much time passed between two moments. From 9:30 a.m. to 2:15 p.m., how much time elapsed? From 9:30 to noon is 2.5 hours. From noon to 2:15 is 2 hours and 15 minutes, so the total elapsed time is 4 hours and 45 minutes. Breaking the interval into manageable pieces simplifies the calculation. Time zones add another layer of complexity, the world divided into regions where clocks are set to different times, roughly following longitude. Traveling east, time zones advance, the clock jumping forward. Traveling west, time zones retreat, the clock jumping backward. This reflects Earth's rotation toward the east, causing sunrise to occur earlier in eastern locations. Thinking about time as you rest, you might imagine clock hands moving smoothly around the face, minutes accumulating into hours, hours accumulating into days, the steady progression of measurable moments. Measurement is humanity's way of quantifying the physical world, assigning numbers to dimensions, masses, and capacities. Different systems of measurement have developed throughout history, but the two most common today are the metric system, based on powers of 10, and the imperial or customary system, using varied conversions like 12 inches per foot and 16 ounces per pound. The metric system's elegance lies in its decimal structure. The basic unit of length is the meter, roughly the distance from a doorknob to the floor. 1 kilometer is 1,000 meters, useful for measuring long distances like roads between cities. 1 centimeter is 1/100th of a meter, useful for measuring small objects like the width of a finger. 1 millimeter is 1,000th of a meter, used for very small measurements like the thickness of a coin. The prefixes kilo, centi, and milli attach to various base units, always meaning thousand, hundredth, and thousandth, respectively. Weight, more precisely mass, is measured in grams in the metric system. 1 kilogram is 1,000 grams, about the weight of a liter of water. 1 milligram is 1,000th of a gram, used for measuring tiny quantities like medication doses. The human body mass might be 60 or 70 kilograms. A car might be 1,000 kilograms. A grain of rice might be 20 milligrams. Volume, the amount of space a substance occupies, is measured in liters in the metric system. 1 liter is the volume of a cube 10 centimeters on each side, roughly a quart. 1 milliliter is 1,000th of a liter, equivalent to 1 cubic centimeter. A soda bottle might contain 2 liters. A teaspoon might hold 5 milliliters. The customary system uses feet and inches for length, pounds and ounces for weight, gallons and cups for volume. 12 inches equal 1 foot, 3 feet equal 1 yard, 16 ounces equal 1 pound, 8 ounces equal 1 cup, 2 cups equal 1 pint, 2 pints equal 1 quart, 4 quarts equal 1 gallon. These conversions lack the decimal regularity of the metric system, but they are familiar to those raised using them. Converting within a measurement system requires multiplication or division by the conversion factor. To convert 5 meters to centimeters, multiply by 100, giving 500 centimeters. To convert 3,000 grams to kilograms, divide by 1,000, giving 3 kilograms. To convert 4 feet to inches, multiply by 12, giving 48 inches. Converting between systems requires knowing the conversion factors. 1 inch equals approximately 2.54 centimeters. 1 pound equals approximately 0.45 kilograms. 1 gallon equals approximately 3.79 liters. These conversions are less tidy because the systems developed independently with different standards. Understanding measurement allows us to quantify and compare, to know whether something will fit, whether we have enough, whether one option is larger or heavier than another. Recipes require measuring ingredients, construction requires measuring materials, medicine requires measuring doses, travel requires measuring distances. Measurement is practical mathematics applied to the physical world. Money is a human invention for storing value and facilitating exchange, and mathematics is essential for managing money wisely. Understanding how to calculate with money, how to compare prices, how to understand interest and growth, these skills contribute to financial well-being throughout life. Most currency systems divide into a main unit and fractional units. Dollars divide into cents, 100 cents per dollar. Euros divide into cents the same way. Pounds divide into pence, again 100 per pound. This decimal structure makes calculations straightforward. Adding and subtracting money amounts uses the same process as adding and subtracting decimals, keeping the decimal point aligned. If you have $23.50 and spend $8.75, subtract to find you have $14.75 remaining. Making change is reverse subtraction. If an item costs $7.30 and you pay with a $10 bill, the change is $10 minus $7.30, which equals $2.70. Cashiers often count up to make change, starting at the cost and adding coins and bills until reaching the amount paid. Unit prices allow comparison of value when products come in different sizes. If a 12-ounce box costs $3, the price per ounce is 3 divided by 12, which equals 25 cents per ounce. If an 18-ounce box costs $4.50, the price per ounce is $4.50 divided by 18, which equals 25 cents per ounce. These products cost the same per unit, neither offering better value. Unit price comparison requires division and careful attention to units. Percentages are crucial in finance. Sales tax is a percentage added to prices, often 5 to 10% depending on location. A $50 purchase with 8% tax requires calculating 8% of $50, which is $4, making the total $54. Discounts subtract a percentage. A $40 item on sale for 25% off reduces by $10, 25% of $40, costing $30 after discount. Simple interest is calculated as a percentage of principal over time. If you save $100 at 5% annual interest, after 1 year you earn 5% of $100, which is $5. Your balance grows to $105. After another year, if interest is simple, you again earn 5% of the original $100, another $5, reaching $110 after 2 years. Compound interest, more powerful, calculates interest on the accumulated total. After the first year, your $105 earns 5%, which is $5.25, bringing the balance to $110.25. Each year, the interest earns interest, creating accelerating growth.
A ratio compares two quantities, expressing their relative sizes. If a recipe calls for 2 cups of flour and 1 cup of sugar, the ratio of flour to sugar is 2 to 1, written as 2:1. This means for every 2 parts flour, there is 1 part sugar, a relationship of doubling. Ratios do not specify absolute amounts, only relative proportions. A ratio of 2 to 1 could mean 2 cups to 1 cup, or 4 cups to 2 cups, or 10 cups to 5 cups, all maintaining the same proportional relationship. Equivalent ratios are like equivalent fractions, different expressions of the same relationship. The ratio 2 to 3 is equivalent to 4 to 6, 6 to 9, 8 to 12. Any pair where the first number is 2/3 of the second. Simplifying ratios involves dividing both numbers by their greatest common factor, just as with simplifying fractions. The ratio 12 to 18 simplifies to 2 to 3 by dividing both by 6. Rates are special ratios comparing different kinds of units. Speed is a rate comparing distance to time, like 60 miles per hour or 30 meters per second. Price per unit is a rate comparing cost to quantity, like $3 per pound or 50 cents per ounce. Rates help us compare efficiency and value across different contexts. Proportions state that 2 ratios are equal, creating an equation we can solve. If 3 apples cost $2, how much do 12 apples cost? We set up a proportion. 3 apples over $2 equals 12 apples over unknown dollars. Cross-multiplying gives 3 times unknown equals 2 times 12. So 3 times unknown equals 24, so unknown equals 8. 12 apples cost $8. This proportional reasoning appears constantly. If a car travels 120 miles in 2 hours, how far does it travel in 5 hours at the same speed? Set up the proportion. 120 miles over 2 hours equals unknown miles over 5 hours. Solving gives unknown equals 300 miles. The proportion assumes the speed stays constant, a steady rate maintained over time. Scale drawings and maps use proportional thinking. If a map scale is 1 inch equals 10 miles, then 3 inches on the map represents 30 miles in reality, and half an inch represents 5 miles. The ratio between map distance and real distance remains constant throughout the map, allowing us to measure any distance by measuring on paper and multiplying by the scale factor. Mixing solutions in chemistry, following recipes in cooking, creating models in architecture, these all use proportional reasoning. The relationships remain consistent even as absolute amounts scale up or down. This consistency is comforting, showing that patterns persist across scales.
A sequence is an ordered list of numbers following a pattern or rule. Understanding sequences means recognizing the rule and predicting what comes next, an exercise in pattern recognition that is both mathematical and meditative. Arithmetic sequences increase or decrease by a constant amount each step. The sequence 3, 7, 11, 15, 19 is arithmetic with common difference 4. Each term is 4 more than the previous term. To find the next term, add 4. 19 plus 4 equals 23. To find the 10th term without listing all terms, we can use a formula, the first term plus the common difference times one less than the term number. The first term is 3, common difference is 4, so the 10th term is 3 plus 4 times 9, which is 3 plus 36, which equals 39. Geometric sequences multiply by a constant factor each step. The sequence 2, 6, 18, 54 is geometric with common ratio 3. Each term is 3 times the previous term. To find the next term, multiply by 3. 54 times 3 equals 162. Geometric sequences grow much faster than arithmetic sequences when the ratio exceeds 1, exponential growth compared to linear growth. Some sequences follow more complex patterns. The sequence 1, 1, 2, 3, 5, 8, 13 is the Fibonacci sequence, where each term is the sum of the two preceding terms. To find the next term, add the last two. 8 plus 13 equals 21. This sequence appears in nature with surprising frequency, suggesting it represents an optimal growth pattern in certain biological contexts. Square number sequences list the perfect squares 1, 4, 9, 16, 25, 36. Each term is a whole number squared. The differences between consecutive squares are the odd numbers 3, 5, 7, 9, 11, revealing a hidden relationship between squares and odd numbers. This pattern can be visualized geometrically by adding L-shaped borders around squares to create the next larger square. Triangular numbers count dots arranged in triangular patterns 1, 3, 6, 10, 15, 21. Each triangular number is the sum of consecutive whole numbers starting from 1. The fourth triangular number is 1 plus 2 plus 3 plus 4 equals 10. Triangular numbers relate to arithmetic series, the sums of arithmetic sequences. Recognizing sequence types allows prediction and generalization. If you see a sequence and identify it as arithmetic, you know each term is a fixed amount larger than the previous, and you can calculate future terms easily. If geometric, you know each term is a fixed multiple of the previous, and exponential growth is occurring. Sequences model real-world phenomena. Population growth might follow geometric sequences if each generation multiplies by a constant factor. Savings accounts with compound interest follow geometric sequences, the balance multiplying by 1 plus the interest rate each period. Arithmetic sequences model situations with constant change, like objects falling under gravity or accounts earning simple interest.
One of mathematics' most famous and useful relationships is the Pythagorean Theorem, a statement about right triangles that has fascinated mathematicians for over 2,000 years. A right triangle has one 90-degree angle called the right angle. The side opposite the right angle is the longest side, called the hypotenuse. The other two sides are called legs. The Pythagorean theorem states that the square of the hypotenuse equals the sum of the squares of the legs. If we label the legs A and B and the hypotenuse C, the theorem says A squared plus B squared equals C squared. This simple equation encodes a profound geometric truth. Consider a right triangle with legs of length 3 and 4. According to the theorem, the hypotenuse squared should equal 3 squared plus 4 squared, which equals 9 plus 16, which equals 25. Therefore, the hypotenuse equals the square root of 25, which equals 5. We can verify this by measuring. A triangle with sides 3, 4, and 5 does indeed form a right angle. This 3, 4, 5 triangle is the most famous Pythagorean triple, a set of 3 whole numbers satisfying the theorem. Other Pythagorean triples include 5, 12, 13, 8, 15, 17, and 7, 24, 25. These triples were known to ancient builders who used them to construct right angles.
By marking a rope at length 3, 4, and 5 units and stretching it into a triangle, they could guarantee a right angle without needing sophisticated measuring tools. The theorem applies regardless of the leg lengths. A right triangle with both legs equal to 1 has hypotenuse squared equal to 1 plus 1, which equals 2. So the hypotenuse equals the square root of 2, approximately 1.414. An isosceles right triangle like this has a specific character. Its two base angles each 45 degrees, symmetry creating elegant proportions. The Pythagorean theorem has countless applications. To find the distance between 2 points on a coordinate plane, we construct a right triangle with legs parallel to the axes, and use the theorem to calculate the hypotenuse, which is the direct distance. To determine if a triangle is a right triangle, we check if the sides satisfy the theorem. To find an unknown side length in a right triangle, we substitute the known sides into the theorem and solve. Proofs of the Pythagorean theorem number in the hundreds, each offering a different perspective on why the relationship holds. Some proofs use areas, showing that the area of a square built on the hypotenuse equals the sum of areas of squares built on the legs. Some use similar triangles, exploiting proportional relationships. Some rearrange shapes algebraically. The multitude of proofs suggests the theorem touches something fundamental about geometric space. Contemplating the Pythagorean theorem before sleep, you might visualize right triangles of various sizes, the relationship between the sides always consistent, always predictable. A mathematical law as reliable as gravity, as constant as the stars.
Symmetry is a property of shapes where one part mirrors another, creating balance and harmony. Recognizing symmetry is deeply satisfying to human perception, perhaps because so much of nature displays symmetry, from butterfly wings to human faces, from flowers to snowflakes. Line symmetry, also called reflective symmetry, occurs when a shape can be folded along a line so that both halves match perfectly. The fold line is called the line of symmetry or axis of symmetry. A square has 4 lines of symmetry, 2 through opposite sides midpoints and 2 through opposite corners. A rectangle that is not a square has 2 lines of symmetry, both through midpoints of opposite sides. An isosceles triangle has 1 line of symmetry running from the vertex angle to the midpoint of the base, the fold that makes the 2 equal sides match. An equilateral triangle has 3 lines of symmetry, 1 through each vertex perpendicular to the opposite side. A circle has infinite lines of symmetry, every diameter being a line of symmetry, the circle being perfectly symmetric in all directions. Some shapes have no line symmetry at all. A scalene triangle with no equal sides cannot be folded to make any 2 parts match perfectly. Such shapes are asymmetric, lacking balance in any direction, yet they still have their own character, their uniqueness also valuable. Rotational symmetry occurs when a shape looks the same after being rotated less than a full turn. A square has rotational symmetry of order 4, looking identical after 90-degree, 180-degree, or 270-degree rotations. A regular pentagon has rotational symmetry of order 5, looking the same every 72 degrees. A circle has infinite rotational symmetry, looking identical after any rotation. The order of rotational symmetry tells how many positions during a full rotation leave the shape looking unchanged. A 2-leaf propeller has order 2. A 3-leaf propeller has order 3. This concept applies to logos, symbols, wheels, gears, any object designed with rotational regularity. Symmetry is not just aesthetic, but functional. Symmetrical buildings balance loads evenly, reducing structural stress. Symmetrical animals move efficiently, their left and right sides working in coordination. Symmetrical molecules often have specific chemical properties based on their balanced structure. Nature uses symmetry extensively because it represents efficient solutions to design problems.
Snowflakes display six-fold rotational symmetry because of the hexagonal crystal structure of ice. Flowers often have petal counts that are Fibonacci numbers, like 5 or 8, because of growth patterns in plant development. Starfish typically have five-fold symmetry, their arms radiating from a central body. Contemplating symmetry, you might imagine folding shapes along their lines of symmetry, watching halves align perfectly, or spinning shapes and observing positions where they look unchanged, the rotation returning the shape to visual sameness despite the motion. A coordinate plane is a two-dimensional surface where every point can be specified by two numbers, its coordinates, indicating its position relative to two perpendicular reference lines. The horizontal line is the x-axis, the vertical line is the y-axis, and they intersect at the origin, the point where both coordinates are 0. Each point on the plane is written as an ordered pair, x-coordinate first, y-coordinate second, and closed in parentheses. The point 3, 4 means move 3 units right from the origin and 4 units up. The point -2, 5 means move 2 units left from the origin and 5 units up. The point 0, -3 means stay at the origin horizontally and move 3 units down. The x-coordinate tells horizontal position. Positive is right of the origin, negative is left, 0 is on the y-axis. The y-coordinate tells vertical position. Positive is above the origin, negative is below, 0 is on the x-axis. The origin itself is 0, 0, the starting point for all measurements. The coordinate plane divides into 4 quadrants. The upper right quadrant, where both coordinates are positive, is quadrant 1. The upper left, where x is negative and y is positive, is quadrant 2. The lower left, where both are negative, is quadrant 3. The lower right, where x is positive and y is negative, is quadrant 4. These quadrants help describe locations. Plotting points on a coordinate plane is straightforward but requires care. To plot 5, 3, start at the origin, move 5 units right, then 3 units up and place a dot. To plot -4, -2, start at the origin, move 4 units left, then 2 units down and place a dot. Collections of plotted points can reveal patterns. If you plot 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, the points form a straight line. This line represents the relationship y equals 2 times x, every y-coordinate being double the corresponding x-coordinate. Graphing relationships on coordinate planes transforms equations into visual objects. The equation y equals x plus 1, when graphed, produces a diagonal line tilted upward to the right. The equation y equals x squared produces a U-shaped curve called a parabola. Different equations produce different curves, each with characteristic shape. The coordinate plane is named for René Descartes, the philosopher and mathematician who developed this system of using number pairs to specify locations, bridging algebra and geometry. This invention allowed geometric problems to be solved with algebraic techniques and vice versa, unifying two branches of mathematics. Coordinates appear everywhere in modern life. Maps use latitude and longitude, a coordinate system for Earth's surface. Computer screens use pixel coordinates, specifying locations for drawing images. GPS devices use three-dimensional coordinates to pinpoint positions. Understanding coordinates is understanding how to specify and communicate location precisely. When a line is drawn on a coordinate plane, its steepness or slant can be measured numerically as slope. Slope quantifies how much the line rises or falls for each unit of horizontal movement. A steep upward line has large positive slope. A gentle upward line has small positive slope. A horizontal line has 0 slope. A downward line has negative slope, and a vertical line has undefined slope. Slope is calculated as rise over run, the change in y-coordinate divided by the change in x-coordinate between 2 points on the line. If a line passes through 2, 3, and 6, 11, the rise is 11 minus 3, which is 8, and the run is 6 minus 2, which is 4. The slope is 8 divided by 4, which equals 2. This means for every 1 unit you move right, the line goes up 2 units. A slope of 2 indicates fairly steep upward slant. A line through 0, 0 and 4, 2 has rise of 2 and run of 4, so slope is 2 divided by 4, which equals 1/2. For every 1 unit right, the line rises half a unit, a gentler climb. A slope of 1 means the line rises 1 unit for each unit it moves right, a 45-degree angle. A slope of -3 means the line falls 3 units for each unit it moves right, a downward slant. Horizontal lines have slope 0 because they do not rise or fall at all. The rise is 0 regardless of the run. Vertical lines have undefined slope because the run is 0 and division by 0 is undefined. They rise without any horizontal movement, an infinite steepness that cannot be captured by a finite number. Parallel lines have equal slopes. If two lines both have slope 3, they are parallel, rising at the same rate, never intersecting no matter how far extended. Perpendicular lines have slopes that are negative reciprocals. If one line has slope 2, a perpendicular line has slope -1/2. If one line has slope -3, a perpendicular line has slope 1/3. This relationship ensures the lines meet at right angles. Slope connects to real-world concepts like grade on roads. A 6% grade means the road rises 6 feet for every 100 feet of horizontal distance, a slope of 0.06. Steeper grades challenge vehicles and create greater danger. Ramps for accessibility must have gentle slopes, often specified as maximum ratios like 1:12, meaning 1 unit of rise for every 12 units of run. Ski slopes are rated by steepness, green circles for gentle slopes suitable for beginners, black diamonds for steep slopes requiring advanced skill. The concept of slope, originally geometric, has metaphorical extensions. We speak of the slope of change, the rate at which something increases or decreases over time, borrowing the geometric concept to describe abstract trends.
Two shapes are congruent if they have the same size and shape, meaning one could be placed over the other and match perfectly, perhaps after sliding, rotating, or flipping. Congruence means identical in all dimensions, every side length equal, every angle measure equal. Two triangles are congruent if all 3 sides of one triangle match the 3 sides of the other, or if 2 sides and the included angle match, or if 2 angles and the included side match. These criteria, called SSS, SAS, and ASA respectively, guarantee that the triangles are congruent, that every aspect of one matches the other. Congruent shapes are important because they represent exact copies, interchangeable parts, repeatable constructions. In manufacturing, congruent parts ensure that components fit together reliably. In construction, congruent bricks or tiles allow predictable coverage and arrangement. In nature, while perfect congruence is rare, bilateral symmetry creates left and right sides that are approximately congruent. Two shapes are similar if they have the same shape but not necessarily the same size, meaning one is a scaled version of the other, enlarged or reduced proportionally. Similar shapes have corresponding angles equal and corresponding side lengths proportional. Two triangles are similar if all 3 angles of one match the 3 angles of the other, which by the properties of triangles guarantees that the sides are proportional. Similar shapes are everywhere. All circles are similar because they have the same shape, differing only in radius. All squares are similar for the same reason. All equilateral triangles are similar. Photographs are similar to the scenes they depict, smaller but maintaining proportional relationships. Maps are similar to the territories they represent, scaled down but preserving shape and proportion. A photograph of a building is similar to the actual building, the relationships between parts maintained even though the sizes are reduced. Scale factors describe the relationship between similar shapes. If one triangle has sides 3, 4, 5, and a similar triangle has sides 6, 8, 10, the scale factor is 2, the second triangle being twice as large. If the scale factor is 1/2, the second triangle would have sides 1.5, 2, 2.5, half the original size. Understanding similarity allows us to work with models, drawings, and representations that preserve relationships while changing size. Architects create scale models of buildings similar to the final structure but small enough to hold in hand. Engineers test scaled-down prototypes where certain physical relationships remain proportional. Astronomers use scale models of the solar system where planetary sizes and distances are reduced proportionally to fit comprehensible space.
A prime number is a whole number greater than 1 that has exactly two factors, 1 and itself. 2 is prime, divisible only by 1 and 2. 3 is prime, divisible only by 1 and 3. 5, 7, 11, 13, 17, 19, 23. The sequence continues infinitely, though primes become less frequent among larger numbers. 4 is not prime because it has factors 1, 2, and 4, more than the two factors defining primes. 6 is not prime, having factors 1, 2, 3, and 6. Numbers with more than two factors are called composite numbers, meaning they can be composed of smaller factors multiplied together. Every composite number can be expressed as a product of prime numbers, and this prime factorization is unique. 12 equals 2 times 2 times 3, the prime factorization of 12. 30 equals 2 times 3 times 5, its unique prime factorization. 56 equals 2 times 2 times 2 times 7, which can also be written as 2 to the third power times 7. Finding prime factorization involves dividing by the smallest primes repeatedly until only primes remain. To factor 60, divide by 2 to get 30, divide by 2 again to get 15, divide by 3 to get 5, which is prime. So 60 equals 2 times 2 times 3 times 5. This process works for any composite number, revealing the prime building blocks that multiply to create it. Prime numbers are the atoms of mathematics, the fundamental components from which all other whole numbers are built through multiplication. This makes them deeply important in number theory, the branch of mathematics studying properties of numbers. Primes have practical applications in cryptography, the science of encoding information. Large prime numbers and their properties are used to create codes that are extremely difficult to break without knowing the key. The security of internet transactions, encrypted messages, and digital signatures often relies on mathematical problems involving prime factorization. The distribution of primes is irregular and somewhat mysterious. While there are infinitely many primes, they do not appear at regular intervals. Sometimes primes are close together, like 11 and 13, or 17 and 19, called twin primes. Sometimes large gaps appear between consecutive primes. Mathematicians have studied prime distribution for centuries, discovering patterns and regularities, but also encountering deep mysteries that remain unsolved. Contemplating primes has a meditative quality, the search for numbers divisible only by themselves and one, the recognition of these fundamental units, the factorization that reveals hidden structure within composite numbers. Divisibility rules are shortcuts for determining whether one number divides evenly into another without performing full division. These rules rely on properties of the decimal system and provide satisfying patterns for recognition. A number is divisible by 2 if its last digit is even, meaning 0, 2, 4, 6, or 8. This is because multiples of 2 alternate between even and odd, and the last digit determines evenness. 34 is divisible by 2, as is 158, because their last digits are even. A number is divisible by 5 if its last digit is 0 or 5. Multiples of 5 always end in these digits, creating an easy visual test. 125 is divisible by 5, as is 690, both ending in either 5 or 0. A number is divisible by 10 if its last digit is 0. This follows from the place value system, where multiples of 10 have no ones, only tens and higher place values. 40, 200, 3000, all divisible by 10, all ending in 0. A number is divisible by 3 if the sum of its digits is divisible by 3. To test 123, add 1 plus 2 plus 3 to get 6, which is divisible by 3. So 123 is divisible by 3. To test 547, add 5 plus 4 plus 7 to get 16. Then add 1 plus 6 to get 7, which is not divisible by 3. So 547 is not divisible by 3. This rule seems magical, but follows from properties of how numbers are constructed in base 10. A number is divisible by 9 if the sum of its digits is divisible by 9, similar to the rule for 3. To test 819, add 8 plus 1 plus 9 to get 18, which is divisible by 9, so 819 is divisible by 9. This rule also connects to the digit sum property of multiples of 9 mentioned earlier. A number is divisible by 4 if its last two digits form a number divisible by 4. To test 3,124, look at 24, which is divisible by 4, so the entire number is divisible by 4. This rule works because 100 is divisible by 4, so any hundreds and beyond contribute multiples of 4, and only the last two digits affect divisibility. A number is divisible by 6 if it is divisible by both 2 and 3, since 6 equals 2 times 3. Test for even last digit and digit sum divisible by 3. 42 has even last digit and digit sum 6. Both tests pass, so 42 is divisible by 6. These rules transform divisibility from laborious calculation into pattern recognition, engaging visual and logical skills simultaneously. They reveal that numbers carry information in their structure, that digits are not arbitrary, but encode divisibility properties. Practicing divisibility rules is meditative, the mind learning to see patterns, to recognize structure, to find shortcuts through understanding rather than computation.
Estimation is the art of finding approximate answers quickly, useful when exact values are unnecessary or impossible to obtain. Rounding is the process of replacing a number with a nearby number that is simpler or more convenient, often ending in zeros. Together, estimation and rounding provide practical tools for mental mathematics and quick decision-making. Rounding to the nearest 10 means finding the multiple of 10 closest to the given number. 43 rounds to 40 because 43 is closer to 40 than to 50. 47 rounds to 50 because 47 is closer to 50 than to 40. The midpoint, 45, rounds up by convention, giving 50. This rule handles the ambiguous case consistently. Rounding to the nearest 100 follows the same principle but focuses on hundreds. 320 rounds to 300. 380 rounds to 400. 350 rounds to 400 by the upward convention for midpoints. The rounded number provides a simpler approximation, easier to work with mentally. Estimation uses rounding to simplify calculations before performing them. To estimate 37 plus 52, round both numbers to the nearest 10, giving 40 plus 50, which equals 90. The actual answer is 89, very close. To estimate 612 times 9, round to 600 times 10, giving 6,000. The actual answer is 5,508, reasonably approximated. The goal is not exactness, but a quick sense of magnitude. Front-end estimation uses only the leftmost digits, the most significant values. To estimate 473 plus 296, consider only the hundreds. 400 plus 200 equals 600. The actual answer is 769, so the front-end estimate is low but provides a rough sense. More sophisticated estimation might add the tens as well, giving 470 plus 290, which is 760, much closer. Compatible numbers are numbers easy to work with mentally, chosen because they combine nicely. To estimate 489 divided by 62, replace with 500 divided by 50, which equals 10. The actual answer is approximately 7.8, so the estimate gives a rough ballpark. The compatible numbers 500 and 50 are easier to divide mentally than the actual values. Estimation is valuable when shopping, budgeting, planning. If items cost $3.98, $7.12, and $5.49, rounding to 4, 7, and 5 gives a quick total estimate of $16, close to the exact total of $16.59. This allows budget checking without careful calculation. In everyday life, we often care more about approximate values than exact ones. Driving to a destination 237 miles away, we think of it as about 240 miles, or roughly 4 hours at 60 miles per hour. The approximations guide planning without requiring precision.
Exact values matter in some contexts, like engineering tolerances or financial accounting, but approximations suffice for most daily decision-making.